Two parallel current-carrying wires will exert a magnetic force on each other. Now, this force will either be attractive if the wires carry current in the same direction, or repulsive if the wires carry current in opposite directions. Now, the reason for this is the fact that these wires carrying current carry moving charge. And remember, a moving charge generates its own magnetic field. So each of these wires will generate their own magnetic field. And when the two magnetic fields interact, they will interact in such a way as to either exert attractive forces on each other or repulsive forces on each other. Let's explore this behavior by doing an example. Two parallel wires of length L are a distance r apart. One wire carries current I1, and the other wire carries current I2. What is the magnitude and direction of the magnetic force between the two wires if the current in each wire flows in the same direction and in opposite directions? Let's approach this problem by first sketching our two wires. So we have wire 1 on the left, and we have wire 2 on the right. For part A, wire 1 is carrying a current straight up. This will be current I1. Wire 2 is also carrying a current straight up. The two currents are parallel, so this current will be identified as I2. The two wires are separated by a distance r, and they are both a length L. Our goal is to determine the magnetic force on each wire and the direction of this magnetic force. Let's start by determining the direction of the magnetic force. Let's look at a formula for magnetic force. We've seen this formula before for a current-carrying wire. The magnetic force on a current-carrying wire is a product of the current in the wire and the displacement differential crossed with the magnetic field that wire is exposed to. Let's begin by looking at the magnetic force on wire 2 due to wire 1. That magnetic force on wire 2 will be given by the current in wire 2 times the displacement differential for wire 2, and this being along the length of the wire, the limits of integration will go from 0 to L, and this displacement differential will be crossed with the magnetic field generated by wire 1. So in order to determine the direction of the magnetic force, we have to determine the result of the cross product, the direction that the cross product would be between the displacement differential of the current and the magnetic field of wire 1. So in order to do that, well, we already know what the displacement direction of wire 2 is. That's in the direction of the current. I'll just draw that right off to the side here. But now we have to do the direction of the magnetic field due to wire 1, since it's wire 1's magnetic field that's exerting the magnetic force on wire 2. Now we can do this by using the right-hand rule. So we're going to use the version of the right-hand rule where we place our thumb in the direction of current, and we curl the fingers of our right hand around the current. And in doing that, we see that the fingers of our right hand will curl around the current in such a way to generate concentric circles representing the magnetic field. If we were to look at the result of that by looking straight down onto wire 1, we would see that the magnetic field forms concentric circles around wire 1, given by the direction of our right hand. So our right hand, as we look down on wire 1, is circulating in a counterclockwise orientation. So that means we could sketch the magnetic field for wire 1 as being concentric circles about wire 1, and those concentric circles extend out everywhere in space, and the orientation is given by the orientation of the fingers of our right hand. Notice that the magnetic field lines that wire 1 generate will produce a magnetic field that is pointing straight away from us into the screen at the point that that magnetic field line interacts with the current. And if we were to extend this, we would know that the magnetic field of wire 1 will be pointing straight away from us at all points on wire 2. So we now know the direction of the magnetic field of wire 1, and we also know that that magnetic field is uniform, because as we've shown previously using Ampere's law, the magnetic field due to a current-carrying wire has a magnitude equal to the product of the permeability of free space, mu naught, and the wire's current, divided by the circumference of the Amperian loop, or in this case, the circumference of the magnetic field line circulating around the wire at the distance of the point we're interested in. So here is the magnitude of the magnetic field due to wire 1. So what we have to do now is determine the direction of the magnetic force between the current differential in wire 2 and the magnetic field due to wire 1. Looking in our diagram, we see that the displacement differential of wire 2 is straight up. So I will just call this dl vector. And we also know that the direction of the magnetic field due to wire 1 is pointing straight away from us. Now, we could use the right-hand rule, or the version of the right-hand rule that says we place our fingers in the direction of the first vector. In this case, the fingers will be in the direction of the displacement differential, and then our palm will face the direction of the magnetic field. So oftentimes I'll just curl my palm in that direction to help me face my palm in the correct direction. But the palm will be in the direction of the magnetic field. And then when we stick our thumb out, the thumb points in the direction of the cross product between those two vectors. So let's do that. Let's put the fingers of our right hand in the direction of the displacement differential. So that's the first vector. Here's our right hand, looking at it from the top. There's our knuckles. So our fingers of our right hand are in the direction of the displacement differential of the current. Notice that our palm is facing towards the magnetic field. Our thumb is pointing to the left. Because our thumb is pointing to the left, that indicates the direction of the magnetic force. So the magnetic force on wire 2 due to wire 1 is towards wire 1. So let's go ahead and illustrate that. So the magnetic force on wire 2 due to wire 1, going straight towards wire 1. Now we could do the same analysis for the magnetic force on wire 1 due to wire 2. We would do that by just doing the same thing we did before, except this time we are determining the magnetic field of wire 2, which, using the right-hand rule, will form concentric circles around wire 2. So this represents the magnetic field lines circulating around the current of wire 2. And notice these magnetic field lines have a particular orientation. At the location of wire 1, the magnetic field lines are coming straight towards us. So I'll represent that with a series of dots to represent the magnetic field coming straight towards us. This magnetic field is the magnetic field generated by wire 2. Now notice that the current direction is straight up. So that's the direction of our displacement differential. And the magnetic field is coming straight towards us. If we were to use the right-hand rule to figure out the direction of the magnetic force, which is given as the direction of the cross product of the displacement differential and the magnetic field due to wire 2, we would see that when we place the fingers of our right hand in the direction of current and face our palm towards the direction of the magnetic field, we would see that our thumb ends up pointing to the right. So the magnetic force on wire 1 due to wire 2 is pointing straight to the right. And remember, this is the same magnetic force, but opposite in direction as the force on wire 2 from the magnetic field of wire 1. Now, Newton's third law told us this as well, because Newton's third law says the force of interaction between two objects is equal in magnitude and opposite in direction. So as soon as we found the magnetic force on one of the wires, that automatically tells us the magnitude and direction of the magnetic force on the other wire. So this is a confirmation for us of our right-hand rule and Newton's laws being complementary, giving us assurance that we have found that these two wires carrying currents in the same direction will be attractive towards each other.